A beam of sunlight leaves the surface of the sun. It races across the vacuum of space, covering 93 million miles in just 8 minutes. That tiny photon, born in the heart of a star, has just crossed the distance between worlds without slowing, without pausing, without hesitation. But what makes this traveler so special? Why is light the ultimate speed limit of the universe? That is what we are about to discover. Think of light as both messenger and ruler of the cosmos. Every distant star you gaze at tonight is sending you light that left years, centuries, or even millennia ago. The twinkle you see is not the star as it is now, but as it was long before you even existed. In a way, when we look up at the night sky, we are looking into a time machine. Light carries history across space, and with it, the strict law that nothing can outrun its pace. But why does the universe bow to this limit, and not some faster one? That puzzle leads us straight into the very fabric of reality. Imagine you're sitting in a car, driving down a highway. If another car speeds past you, you can measure how much faster it's going compared to you. Speeds add up, right? But when it comes to light, things don't work that way. Whether you're standing still, racing in a jet, or even moving near the speed of light yourself, the beam of light will always seem to move away from you at the exact same speed. 299,792 kilometers per second. This strange rule doesn't just defy our intuition. It reshaped physics itself. And it was Albert Einstein who first explained why. Einstein's theory of relativity revealed that light speed isn't just about light. It's about the structure of the universe. Space and time themselves bend, stretch, and adjust so that the speed of light remains constant. If you move faster, time slows for you. Distances shorten. Reality itself warps, all to preserve that universal speed limit. Light, then, is less like a fast traveler and more like the referee keeping the game of the cosmos fair and consistent. But here's the hook. If time and space can bend for light, what does that mean for us? Fragile beings made of matter? Let's step back and look at the basics. Light is a wave, but it is also a particle called a photon. Unlike us, photons have no mass. And because they have no mass, they are free from the drag that slows everything else down. A car, a rocket, even the fastest particle in the Large Hadron Collider. Anything with mass requires more and more energy to keep accelerating. Push close to light speed, and the energy demand becomes infinite. In other words, mass is the anchor that holds us below light's limit. Light travels unchained, while we, tied down by matter, can never quite catch it. But does this mean faster than light travel is truly impossible? Or is there a loophole? Here's where science starts to blur into the realm of imagination. Physicists have toyed with ideas like wormholes, warp drives, and hypothetical particles called tachyons that might move faster than light. Each concept teases us with the possibility of breaking the speed limit. But every time we try to push past it, the math rebels. Equations collapse, energy demands explode, and reality itself seems to forbid the attempt. It is as though the universe has locked its doors, whispering, "This far and no further." But if the speed of light is the limit, then how does the universe itself expand faster than light in its earliest moments? That paradox takes us to the mystery of cosmic inflation. After the Big Bang, the universe expanded at a rate faster than light could travel. Galaxies rushed apart so quickly that light had no time to catch up. But this doesn't violate physics, because it wasn't objects moving through space faster than light. It was space itself stretching, carrying everything within it. Light remained the referee, even as the playing field changed beneath its feet. But if light defines reality as we know it, then what happens to light at the edges of the universe? Does it ever stop, or fade, or disappear? Every photon you see, every beam of sunlight, every star's shimmer, it keeps going forever, unless it is absorbed by something. A photon born in the Big Bang itself may still be traveling through space right now. Billions of years later, whispering ancient secrets in the form of cosmic microwave background radiation. That faint afterglow is the oldest light in the universe, a ghostly memory of creation itself. Light doesn't just illuminate the universe. It preserves its memory, keeping a record of everything that ever happened. Which leads to a haunting thought. Are we, right now, sending out our own signals of existence into the future, to be seen by civilizations yet unborn? Imagine it. Every radio broadcast, every flicker of television, every message we beam into the sky is light, racing outward at the universal speed limit. Our presence is being stamped onto the cosmos, perhaps to be intercepted by distant beings thousands or millions of years from now. In a sense, we are all storytellers, and light is carrying our stories across the darkness. But here lies the final twist. If nothing can move faster than light, then it also means there is a horizon we can never cross, a limit to what we can ever see or know. The universe, vast as it is, will always keep secrets hidden beyond that unreachable boundary. If the speed of light is the universe's ultimate speed, then time itself bends around this strange law. Imagine a spaceship hurtling close to light speed. To the passengers inside, time flows normally. They eat, they talk, they age. But to an observer back on Earth, their clock ticks slower, their heartbeat stretches out, their very lives seem to move in slow motion. This is not science fiction. It's been measured with particle beams and atomic clocks. The faster you go, the slower time passes. And at light speed, time itself freezes. A photon, then, experiences no time at all. For light, there is no past, present, or future, only eternal motion. But what does it mean to exist in a universe where time itself has a speed limit? This idea leads to one of the most profound consequences of relativity, the concept of the light cone. Picture a flashlight shining in the darkness. Its beam spreads outward in all directions, forming a cone of illumination. In physics, this cone represents all the events that light could possibly reach in the future, and all the events whose light could possibly reach you from the past. Anything outside that cone is forever disconnected from you. No signal, no message, no cause or effect can cross that forbidden region. The light cone is the boundary between what is possible and what is forever unreachable. But here's the chilling thought. Every moment of your life is surrounded by this invisible boundary, shaping what you can ever see, touch, or influence. The light cone also defines the edge of our observable universe. We often say the universe is 13.8 billion years old, but when we look into deep space, the farthest galaxies we can see are about 46 billion light years away. How is this possible? Because as light traveled toward us, space itself stretched, carrying galaxies farther and farther apart. The light finally arrived, but the galaxies that emitted it are now much farther away than they were. The observable universe is like a bubble, defined not by how far things are, but by how far light has had time to travel. But beyond that bubble lies a vast, unseen realm that light will never reach. And so, we are trapped inside a cosmic horizon, looking out but never beyond. For many scientists, this cosmic limit is both frustrating and awe-inspiring. On one hand, it means there will always be mysteries forever hidden from us, galaxies that exist but can never be seen, events that unfold beyond the reach of light. On the other hand, it makes everything we can see that much more precious. The stars, nebulae, and galaxies that sparkle across the night sky are not random. They are the chosen few whose light has made the long journey across the darkness to meet our eyes. Every photon is a survivor, a messenger, carrying ancient news across the abyss. And each one whispers a question. What lies just beyond the edge of sight? But light's role as the cosmic speed limit is not just about distance. It's about cause and effect. If nothing can travel faster than light, then no effect can happen before its cause. Drop a pebble into a pond, and the ripples spread outward at a fixed speed. Light is the universe's ripple, ensuring that reality unfolds in order. If faster than light travel were possible, then effects could leap ahead of causes. You could see the outcome before the action, hear an echo before the sound, even witness your own arrival before your departure. Physics would unravel, and time itself would lose its meaning. Light is not just fast. It is the glue holding reality together. But could there be cracks in this glue? Places where the rules bend? One fascinating test of this boundary comes from black holes. Imagine a star so massive that when it collapses, its gravity becomes irresistible. Even light, racing at the maximum speed of the universe, cannot escape. The edge of this region is called the event horizon. Anything crossing it, matter, energy, or information, vanishes from the observable universe forever. To us, the event horizon is the ultimate boundary. To light, it is the end of the road. But this creates a paradox. If information is lost inside a black hole, does it mean the universe itself loses track of its own history? Some of the brightest minds in physics, from Stephen Hawking to modern theorists, have struggled with this puzzle. And once again, light is at the heart of the mystery. Think also of the quantum world, where particles behave in strange, unpredictable ways. In quantum entanglement, two particles separated by vast distances can influence each other instantly, as if connected by an invisible thread. Does this mean information can travel faster than light? Not quite. The entangled particles share a hidden link, but no usable signal passes between them faster than light. The universe seems to allow strange correlations, but it never breaks its own speed limit. Light remains the ultimate referee, even in the bizarre theater of quantum physics. But if light is both particle and wave, both messenger and barrier, could we ever truly harness it to travel the stars? Science fiction often dreams of faster-than-light ships, warp drives, hyperspace, stargates. And while imagination has no limits, physics keeps reminding us of the cost. To push even a small spaceship to near-light speeds would take more energy than the sun produces in years. The universe doesn't forbid dreams, but it does charge an impossible price. Still, these dreams inspire real science. The concept of a warp drive, for example, doesn't move a ship faster than light. Instead, it bends space itself, contracting space ahead and expanding it behind. The ship never breaks the speed limit. It simply lets space do the moving. This idea is still theoretical, but it shows how human curiosity pushes against the walls of reality, searching for cracks in the cosmic code. In the end, light remains the silent ruler of the universe. It defines distance, it defines time, and it defines the boundaries of knowledge itself. Every law of physics, every corner of reality, seems to bend around its constancy. We live in a universe where nothing can outrun light, and that simple fact shapes everything we know. But there's a deeper question still lingering. Why this speed? Why not faster or slower? Why did the fabric of reality choose this particular number, 299,792 kilometers per second, as the maximum pace of existence? That mystery will lead us deeper into the very foundations of physics, and perhaps into the hidden architecture of the cosmos itself. When we hear the number 299,792 kilometers per second, it sounds oddly specific, almost arbitrary. Why this speed and not something else? Why didn't the universe choose a round number, like 1 million kilometers per second? To understand, we must realize something profound. The speed of light is not just about light. It is a property of space and time themselves. Photons merely reveal the rule that was already written into the fabric of reality. In other words, the speed of light is the universe's way of showing us how space-time behaves. But how can empty space decide the fastest speed in existence? To answer this, let's step into the world of Maxwell's equations, the laws that describe electricity and magnetism. In the 1800s, James Clerk Maxwell discovered that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This dance between electricity and magnetism produces waves, electromagnetic waves, that ripple through space. When Maxwell worked out the math, he found that these waves always traveled at a fixed speed. And when he compared the number to experiments, it was identical to the speed of light. This was the first hint that light is an electromagnetic wave, and that its speed comes not from the properties of light itself, but from the very structure of space. So light speed is not random. It is woven into the geometry of the cosmos. But what else might be hidden in that geometry? Think of space as a kind of fabric with tension. Just as waves on a string depend on the string's properties, its tension and density, so the speed of electromagnetic waves depends on the tension of space itself. In this analogy, the permittivity and permeability of free space, two fundamental constants, set the limit. Light speed is simply the natural result of how empty space responds to electric and magnetic fields. This is why the number feels so precise. It's not chosen, it's discovered. Light is moving at the only speed the universe will allow. But if space-time itself sets the limit, then it means light speed is also the speed at which information itself can move. This brings us to one of the most important truths in physics. The speed of light is not just about motion, but about causality. Imagine trying to send a message to a distant galaxy. No matter how powerful your signal, no matter how advanced your technology, your message cannot arrive faster than light. This enforces a universal order of events, a chain of cause and effect that no one can break. Faster than light communication would mean receiving answers before questions, or seeing explosions before causes. Reality would unravel. So light is not merely fast. It is the protector of logic itself. But could there be hidden realms where causality breaks down? Some theories suggest that deep inside black holes, or at the very beginning of the Big Bang, the rules of space-time may behave differently. At singularities, where density becomes infinite, light's role as the speed limit may collapse. The laws we know may no longer apply. If so, then perhaps the universe was born in a moment when causality itself was undefined, and light had not yet claimed its throne. Only when space and time stabilized did light become the enforcer of order. This thought is both thrilling and unsettling. Perhaps the speed of light is not an eternal law, but a rule that emerged after chaos. But if that is true, then could the universe ever change the rule again? To test these possibilities, physicists have searched for tiny cracks in light's constancy. They have measured the speed of light from distant galaxies, from supernova explosions, even from ancient gamma-ray bursts. If light speed had changed over billions of years, we would see distortions in the arrival times of different photons. But every test comes back the same. Light is stubbornly constant, unwavering, faithful. It is as though the universe built this law into its foundation, ensuring it would never falter. And yet, there is still a mystery. Why do these constants, like the permittivity and permeability of space, have the values they do? Could they have been different in another universe? Here we stumble into the realm of the multiverse hypothesis. Some scientists imagine that our universe is just one bubble among many, each with its own laws of physics. Perhaps in another cosmos, the speed of light is slower or faster, or perhaps light doesn't exist at all. If true, then our universe is simply one possible version of reality. And the reason we find ourselves here is that this version allows life to exist. If light were slower, stars might not burn long enough to support planets. If it were faster, atoms themselves might not hold together. The speed of light may not be random at all. It may be the delicate tuning that makes existence possible. But is this deep design or pure chance? The question stretches beyond science into philosophy. Why should the universe allow order at all? Why should there be laws rather than chaos? And why should those laws be expressed in something so elegant as light, the very thing that lets us see and know the world? For thousands of years, humans have equated light with truth, with knowledge, with divinity itself. And now, science tells us that light is indeed the boundary of all knowledge, the speed limit of existence. In a way, ancient symbolism and modern physics converge. Light is not just a metaphor for truth. It is the literal truth that defines our universe. But here lies one last mystery. What happens at the edge of light, when we reach the horizon of the knowable? Imagine standing at the shore of a vast ocean, watching the waves stretch to the horizon. Beyond that horizon, you know there is more ocean, but you can never see it. That is what light does to our universe. It gives us a horizon, a limit, a final curtain beyond which our instruments cannot reach. We may theorize, we may dream, but we will never see beyond it. And perhaps that is the universe's greatest secret, that mystery itself is built into its design. Light shows us much, but it also keeps some truths forever hidden. And in that balance of revelation and mystery, the universe reminds us of our place, small, curious, and forever reaching toward the light. Long before scientists measured its speed, long before equations revealed its nature, Light was already at the center of human imagination. To our ancestors, fire was not just warmth, it was survival, a sacred flame that pushed back the darkness. Light became a symbol of safety, of knowledge, of the divine. Ancient myths across cultures told of gods who commanded the sun, of heroes who stole fire from the heavens. Even without knowing its true nature, humans sensed that light was different, powerful, elusive, untouchable. It was the bridge between heaven and earth. But as centuries passed, we began to ask not just what light symbolized, but what it really was. The first great debates were simple yet profound. Was light made of particles, as Isaac Newton believed, or was it a wave, as Christian Huygens argued? The struggle between these ideas lasted for centuries. Experiments with mirrors, prisms, and water tanks revealed light bending, splitting, and interfering with itself, behaving like a wave. And yet, the photoelectric effect showed that light sometimes acted like discrete packets or photons. Light refused to be pinned down, living in two worlds at once. This dual nature became the heart of quantum mechanics, forcing us to abandon intuition and accept a reality stranger than imagination. But the very act of studying light brought us closer to understanding the universe's speed limit. Consider the first measurements of light speed. In the 1600s, Ole Romer observed the moons of Jupiter and noticed delays in their eclipses depending on Earth's position. From this, he estimated that light had a finite speed, an astonishing revelation in a time when many still believed it was instantaneous. Later, experiments on Earth confirmed it, bouncing light off mirrors or sending it through rotating gears. Each test brought us closer to the exact number, 299,792 kilometers per second. With every refinement, humanity was learning not just how fast light was, but how the universe itself kept order. But knowing the speed of light was only the beginning. The next step was learning how to control it. From torches to lanterns, from candles to gas lamps, our history is marked by our attempts to capture and tame light. But the true revolution came with electricity. Suddenly, light could be summoned at will, glowing in bulbs, spreading across cities, turning night into day. The human relationship with darkness was forever changed. No longer bound by the cycles of the sun, our world became a 24-hour civilization. And with lasers, light concentrated into perfect beams, we gained tools of extraordinary precision, used in everything from surgery to space exploration. Light became not just illumination, but technology, medicine, and communication. But the most powerful leap came when we used light not just to see, but to send information. Fiber optic cables, carrying pulses of light across oceans, now bind our world together. Every message, every video call, every signal zipping across the globe rides on beams of light. racing through glass threads at nearly the universal speed limit. In a sense, we already live in an age where humanity communicates at light speed. Our words and thoughts travel across continents almost instantly, limited only by the same rule that governs the cosmos. Light has become our messenger, not just from stars, but from ourselves to ourselves. But even as we mastered light on Earth, we dreamed of bending it for travel among the stars. This dream led to some of the boldest concepts in physics. The idea of the warp drive, for example, doesn't try to make a ship outrun light. Instead, it imagines bending space itself, compressing it ahead, stretching it behind, and letting the ship ride the wave. To an outside observer, the ship would appear to move faster than light, but in truth, it would never break the speed limit locally. In theory, this sidestep preserves relativity's rules while opening the door to interstellar voyages. But in practice, the energy requirements are staggering, perhaps needing more energy than the universe itself contains. For now, warp drives remain in the realm of speculation. Yet the very act of thinking about them shows humanity's restless urge to push against the boundaries light has drawn. And it's not just warp drives. Wormholes, hypothetical tunnels through space-time, offer another possible loophole. If one end of a wormhole connects two distant points in space, stepping through could allow near-instantaneous travel, bypassing light's long road. But once again, the math grows unstable, requiring exotic matter with negative energy. We have not found such matter, and perhaps never will. Still, the very idea reveals something profound. We are creatures who refuse to accept limits quietly. Where light says no further, our minds whisper, "What if?" And sometimes that whisper becomes discovery. Indeed, every step forward in physics has come from questioning light. Einstein's relativity emerged from wondering how the world looks when chasing a beam of light. Quantum mechanics arose from puzzling over how light can be both particle and wave. Even modern theories of the universe's structure, dark energy, cosmic inflation, the search for unification, all circle back to how light interacts with space-time. It seems the speed limit of the universe is also the key to unlocking its deepest mysteries. And so, by studying light, we are not just learning about brightness or speed. We are learning about reality itself. But perhaps the greatest mystery of all is not how fast light moves, but what it really is. Because when you strip away the equations, the constants, and the technology, light remains something deeply mysterious. It is the dance of electromagnetic fields, yet also the photon particle. It is timeless, yet it defines time. It carries information across the universe, yet it has no mass. Light is everywhere, yet it is also fleeting, constantly absorbed, re-emitted, reshaped. We chase it, we trap it in lasers, we measure it to decimals, but it still feels like something otherworldly. And maybe that's why humans have always treated light with reverence. From fire-worshipping rituals to modern physics labs, light is our companion, our teacher, and our boundary. But what happens when we look beyond even light itself? That question takes us to the final step of our journey, the horizon of the universe, where light defines not only what we can see, but what we can never see. If the speed of light is the universe's ultimate speed, then it is also the edge of knowledge itself. Beyond that limit lies mystery, untouched, unreachable, forever beyond. And yet, the human spirit has always leaned toward the unreachable. The story of light is the story of curiosity, of a species forever chasing the horizon. And as long as we keep asking, light will keep guiding us, reminding us of the limit, but also illuminating the path forward. When we step outside on a clear night, the stars above seem eternal, fixed, and serene. Yet what we are really seeing are messages, photons that have traveled for years, centuries, even billions of years before finally reaching our eyes. Each tiny spark of starlight is a survivor, a traveler that has crossed unimaginable distances to tell us a story. And this is the quiet magic of light. It is both the messenger and the message, carrying with it the history of the cosmos. Without light, the universe would remain invisible, silent, unknowable. But with light, the darkness becomes a library of time. Every star, every galaxy, every flicker of light is a page, waiting to be read. But if light is our messenger, then it is also our gatekeeper. The same law that allows us to glimpse the distant past also limits how far we can see. Beyond a certain horizon, the light has not had time to reach us, and never will. There are galaxies, perhaps entire clusters of universes, that we will never know about, not because they do not exist, but because their light can never arrive. The universe, in this sense, is both generous and cruel. It gives us beauty to behold, but it also places a curtain at the edge of vision. And so, light is not just the speed limit of the cosmos. It is the edge of our curiosity. We can imagine beyond it, but we can never touch it. Yet maybe this boundary is not a flaw, but a gift. Boundaries shape us. Just as a horizon makes us long to explore, the speed of light gives us something to strive against. If we could see everything, if we could know everything instantly, perhaps curiosity itself would wither. But the universe whispers its secrets slowly, at the pace of light, and in doing so, it keeps us wondering. It keeps us searching. It keeps us reaching for answers. In this way, the limit is also the invitation. Light says, you cannot see everything now, but you can try. And this, perhaps, is why humanity has flourished, because we are never content with what we know. We are forever chasing what lies just beyond the glow. And in that chase, light has become our partner in ways more intimate than we often realize. Every photograph ever taken is frozen light. Every memory of a sunset, every flicker of a candle, every glimpse of a loved one's face. All of it is light captured by our eyes and etched into our minds. Our very perception of reality is shaped by the photons bouncing into our retinas. In a very real sense, light is not just outside of us. It is us. The atoms in our bodies were forged in stars, released as light and matter, recycled across the cosmos until they became part of you. Sitting here, listening now. Light is both the boundary we cannot cross and the thread that connects us to everything. This duality is what makes light so mysterious. It defines time and space, yet it is also timeless and spaceless. It is the fastest thing in the universe, yet it feels gentle, almost fragile, when it touches our skin. It is everywhere, yet impossible to hold. It obeys precise laws, yet it slips through our understanding. Perhaps this is why light has always been more than just a physical phenomenon. It has been a symbol of knowledge, of awakening, of the eternal. Philosophers have called it truth. Religions have called it divine. Scientists have called it a constant. And in every case, light has lived up to its role as the bridge between mystery and understanding. But as we reflect on all this, a humbling truth emerges. Light is not eternal for us. Stars will fade, galaxies will dim, and even the photons streaming across the cosmos will eventually stretch beyond usefulness as the universe expands. Someday, far in the future, the night sky will go dark as distant galaxies slip beyond the cosmic horizon. Civilizations then, if any remain, will live under skies far emptier than ours. For them, the universe will appear smaller, lonelier, stripped of the light we take for granted. And yet, even in that fading, light will remain what it has always been. The speed limit, the final law, the silent ruler of existence. But in our age, here and now, we still live in the golden time of light. We are lucky. We can look up and see galaxies billions of light years away. We can measure photons born at the dawn of time. We can send beams of light into space, knowing they will carry our presence long after we are gone. And we can marvel that this simple, mysterious constant, the speed of light, shapes the story of everything. Light tells us that we are small, yet connected to the infinite. It tells us that there are limits, yet invites us to keep reaching. It tells us that the universe has a speed, and in honoring that speed, we learn the rhythm of reality itself. So perhaps the real beauty of light's speed limit is not that it stops us, but that it defines us. Without it, there would be no time, no causality, no structure to the universe. Without it, the cosmos would not unfold as a grand story, but as a chaotic blur. Light is not just the speed of the universe. It is the heartbeat of existence. And as long as it shines, we too will continue our journey, forever reaching toward the horizon. forever chasing the light, and forever reminded that in its glow lies both our boundary and our destiny.